Welcome back, Chemistry 30. This is the second booklet in the acids and base section, dealing with 19.2 strengths of acids and bases. So what we're looking at here are strong acids versus weak acids, acid ionization constant, strong bases, weak bases, and base ionization constant. Relate the strength of an acid or base by its degree of ionization. Compare the strength of weak acids and strength of its conjugate acid, and vice versa. And explain the relationship between strengths of acids and bases and the value of their ionization constants. Then lastly, compare the strengths of the dissociations in the series of polyprotic acid. So first of all, the difference between strong acids and weak acids. With strong, we assume that it's almost 100% ionization or dissociation or breaking down. So if we have an acid HX, where X is just some negative ion, as you can see by the length of the arrow, most of the equilibrium exists in this region. So most product exists instead of reactant. And the amount of H plus ions that are left free make it a strong acid. Whereas a weak acid, most of the acid exists in the undissociated form, the unionized forms. So there's very few H plus ions floating around, giving it a strong acid characteristic. Okay, if we look over here, also the more H ions you have floating around, the stronger the electric current could be, the better a conductor it is, the easier it can transmit electric current. And of course, a strong acid will have a weak conjugate base, since the equilibrium lies mostly on the conjugate base side. So strong acid has a weak conjugate base, which makes sense because a strong acid, most of it exists on this side. So X going back and forming HX, receiving the H, it won't happen very frequently because you can see only a small part of it goes that way. So a strong acid will have a weak base. And vice versa, a weak acid will have a strong conjugate base. So if we look over here, a weak acid, its base is X. How much X will receive H's to make HX? A lot, because you can see the arrow exists on this side. So strong is paired up with weak, and weak is paired up with strong, basically there. Why does the Bronston-Lowry not help, or what does the model not provide? It doesn't give any quantitative, doesn't give anything in terms of numbers, how strong or weak something is. So if we look at it, we're going to derive the acid constant. It's very similar to how we developed the equilibrium constant. So for example, here I have HSCN, the acid, combined with water to make H3O plus and Cn minus. So products over reactants, as you can see here. Now what we do here is we combine the water concentration with KEQ, because it's not going to, these little acid characteristics, their changes are very small considering how much water you have. So it's combined with KEQ to give us our new variable Ka, or acid constant. So it's this products over reactants again, but with no concentration of water there. So strong acids would have a high Ka value because most of it exists on the right hand side if it's strong. It's mostly dissociated, which means a lot of products, fewer reactants. So as you can see, we'd have a high value here. Large numerator versus small denominator would give you a large number overall. Okay, so we'll take a look at a couple of questions here. So what is the equation first of all, and then figuring out the Ka expression. So I would tell you, if we're dealing with an acid or a base here, HS negative, we'll say it's an acid. So if it's an acid, it donates its hydrogen to water. Water needs to become H3O plus. In order to do that, loses an electron to make room for that H to attach. And then S minus would have lost its electron with the H, so it gains one, etc. So that would be the equation, and then the Ka would be products over reactants except exclude water. So H3O plus multiplied by S2 minus over HS minus. Next question, what about the third ionization of phosphoric acid? So if you take a look what I mean by the third ionization, phosphoric acid looks something like this, H3PO4. So if it ionizes once, loses one hydrogen to become that, loses another hydrogen to become that, loses its last hydrogen to become PO4 3-. So the third ionization would be picking up where we left off here. HPO4 2-, its hydrogen goes to water. Again, water becomes the hydronium ion, H3O+. Here we'll be left with a blank space, which is taken up by electron, making that charge go one more negative. And of course, the Ka equation, products over reactants, except don't include water. Strong bases and weak bases, so very similar to acids. Strong bases almost completely ionized in solution, whereas weak are only partially ionized. So very much the same thing there. So here we're dealing with the Kb, a base constant. If we look at this, HCO3- in water, if I had told you it was a base, you know that it accepts a hydrogen ion from water. When it accepts hydrogen, water is now OH. It has an empty spot where that hydrogen was, so we use that negative to fill the gap, as I say there. And over here, HCO3-, we need to make room for that new H, so it loses an electron. So if you remember, if you lose an electron, you get more positive. So if we're at -1, if you look at the new number scale, going from -1, moving one positive position, you'd end up at 0, i.e. no charge. So HCO3- becomes H2CO3. And then the base constant is calculated similarly, products over reactants, but don't include water. Easy. Next, differentiate between dilute and concentrated. If we're just simply speaking relatively to each other, dilute would have a small amount of acid or base dissolved in water, whereas a concentrated solution would have, well, more than that, a larger amount of acid or base dissolved in water. Quite often, the meaning of strong acids or bases and weak acid bases get confused with concentrated and dilute. What's the difference? Remember, strong and weak refers to how much is it ionizing, how many H's are released, or how many OH- ions are made. Whereas concentrated and dilute just simply refer to how much we have dissolved in water. So for example, your stomach has a strong acid, but it's diluted. Strong hydrochloric acid, but a small concentration or very dilute amount of it in your stomach. Okay, so there you have it. We'll look at the vocab here. Strong acid. So again, to rehash that, almost completely ionized in solution. So for example, hydrochloric acid exists mostly as H+ ions and Cl- ions floating around, as opposed to undissociated HCl. Weak acid, only partially ionized in solution. So for example, acetic acid, which is found in vinegar, it only slightly goes to the right and releases H+ ions. Most of it exists as CH3COOH. Acid ionization constant is the ratio of products to reactants and suggests how strong the acid is. If we get a big value, that means most of it was dissociated. High numerator versus small denominator.